Thanks, Liam. So everybody who wasn't here last week, welcome to Singapore. And everybody who was here last week, thanks for giving me another chance. So today I want to talk about randomness. For last time we looked at, given a real number, under what circumstances can you find a continuous measure relative to which that real is random? Right? So today I want to address or look into the question of what if you put constraints, regularity constraints, or other sorts of desirability criteria on the measure, right? Then what happens for the criteria that the sequence be random for a measure that has these better features? So hence the title, Finding Better Randomness. Okay, so what we're going to do today is I want to talk about three topics. The first one is, this is not my work. This is, we'll see, it's Lutz and Doma and Riemann, among others. So measures with the mass distribution property, which is a regularity property with regard to sort of geometric measure theory. The second one is looking at what does it mean to be random. And here there's some fragmentary results, but by no means a complete solution to the question. Measures that have well behaved, they're well behaved with respect to the Fourier Transform and uniform distribution of mass. And lastly, we'll look at how this sort of thing is manifest inside sort of more classical aspects of randomness having to do with normality and exponent of irrationality and other aspects of Diophantine approximation. So that's the agenda today. So to start, so we're going to see, a nice proof of concept of how looking at pointwise randomness and looking at regularity properties of a measure interact with each other. Okay, so Hausdorff, this is looking at Hausdorff dimension, which is a way of assigning size or expanse for sets that are of Lebesgue measure 0. So it's something that's called fractal dimension. Yes, this is maybe familiar to a lot of people in the audience, but there's a nice account of it that we're going to try to generalize as we go ahead. Okay, so Hausdorff dimension is usually defined in terms of open covers or capacity or things like that. If you look at it for sort of after the fact, if you look at it from the point of view of measures, then there's a nice theorem of Frostman's lemma, which says that a set, it establishes a connection between the dimension of a set and the types of measures that set can support. Okay, so we'll take this as a definition. Okay, so for S, a number between 0 and 1, and A, a Borel set, A has Hausdorff dimension at least S, if and only if there's a Borel measure mu and a positive constant C such that A supports the measure mu, and for all reals C and for all positive numbers R, the measure of the ball around C of radius R is less than or equal to C times R to the S. Okay, so think of R as, when R is small, right, then R to the S is larger than R. Like the square root of a number is larger than the number if the number is small. Okay, so you're allowed to concentrate mass, right, but not too much. Right? So it says that a measure like this is called, well, let's see, so it's a measure with this property is called S regular, or you say that the measure has the mass distribution property for S. So you can talk about the dimension of a set in terms of the type of measure that the set supports. Right? And the criteria here is that you don't concentrate too much mass inside small intervals. Right? There's a connection between the actual length of the interval, the size of the interval, and the amount of mass that the measure can assign to that interval. Can't be too much. So, for example, S regular measures are all continuous measures. An S regular measure can't have an atom. right? Because that would assign positive mass to a point, right? Which is completely precluded by this. Okay. Hausdorff dimension of A is the supremum of such S. And if you have a measure that has this property, then for every smaller S, that measure has to give any set of Hausdorff dimension. You have a smaller Hausdorff dimension measure 0. Okay, so good. Okay, so dimension is associated with the support of a measure. For example, the Cantor middle third set. Right? That's where you take the unit interval and knock out the middle third, and then in each of the remaining intervals, knock out the middle third, and so on. Every step along the way, you're throwing away a third of the Lebesgue measure. The limit of that process is a null set, but it doesn't mean that it has no size. Right? It has Hausdorff dimension log 2 over log 3. Right? And the uniform measure, the measure where you take the unit interval and you knock out the middle third, and now you've got 2 pieces left. Give each piece measure a half. Right? And continue that process. That's the uniform measure on the Cantor middle third set. And it is regular with the same exponent as the Hausdorff dimension of the set. So this is a good example to keep in mind. Okay, so now, how do you look at the measure, how do you look at the dimension of a set and compare it to the properties that a random real for that measure would have? Okay, so we want to go from the global property of the set, it supports a measure of a certain type. So what does it tell you about the elements of the set? What is a typical element for an S regular measure? Right? And that's this line of investigation. So the effective Hausdorff dimension is usually defined in terms of, Lutz defined it originally in terms of martingales. Riemann gave a different way in terms of effectively open covers, sort of in the tradition of Martin-Luft randomness, but for an S regular measure. If you want to just look at points, which is what we're looking at, the typical element, right? Then there's a theorem of Meyer-Doma, which says that the effective Hausdorff dimension of a real number C is the infimum of the numbers R such that for infinitely many L, the sequence of the first L digits in the binary expansion of C has prefix-free Kolmogorov complexity less than or equal to R times L. Okay? So that took me 2 breaths to say, but all it says is that if you look at that the information, right, that's sitting inside C is compressible. Right? You can describe the initial segments of C by something that is shorter than the length, and the ratio of compression is this effective Hausdorff dimension. Okay, so what are facts about effective Hausdorff dimension? So the first fact is the set of Xi such that Xi has effective Hausdorff dimension D has Hausdorff dimension D. Okay, so there is the things that have that satisfy that criteria is it's a null set, but it has fractal dimension. It has fractal dimension exactly the same as the compression factor. Okay, second, this is a more recent theorem of Jack and Neil Lutz. If you have a subset of the reals, the Hausdorff dimension of that set is the infimum over all B, so you get to relativize to B. Okay? So relativizing to some sort of optimal real. So the infimum is this optimization. Okay? So relativize to an appropriate B, and then take the supremum of all the effective Hausdorff dimensions relative to B of the elements of A. Okay? And then you get the Hausdorff dimension. So you can look at a set, you can look at somehow optimize if it's a closed set, look at the tree that codes the set. That gives you sort of optimal description. And then you can just, relative to the description of the set, you can look at the soup of all the effective Hausdorff dimensions. And that tells you the Hausdorff dimension of the set A. Okay, so by looking at the elements of A, you can read off the Hausdorff dimension. Okay, so this if you know all this stuff and you want something to think about, and you're willing to accept the suggestion, this looks like a complicated definition. This is you have to look at all the reals B, and then you have to take the soup over all the reals inside A. That looks like it's like a pi 1-2 definition. But in fact, it's an arithmetic property. If you have if A happens to be a closed set, then it's arithmetic in A to figure out what the Hausdorff dimension is. Okay, so here's the theorem that I wanted to say is a good example of a case study, a success, along the lines of what I'm looking for. Okay, so this is a theorem of Jan Riemann's. So it's difficult for me to think of Jan Riemann as having proven an old theorem, but this theorem is, because I think of him still as a graduate student, but so about 10 years ago. So suppose that you have a real that has effective Hausdorff dimension D. Then, right, for every S less than D, there is an S regular measure such that C is one random relative to that measure. Okay? So if you have this property, this sort of recursion theoretic property of the real, right, then you can invert that property to get a measure, right, which is for every S less than D, there is an S regular measure mu such that C is one random relative to mu. So in a way, this is giving you an answer. Right? What properties can you infer about a class of reals? Right? So what properties of the real numbers can you infer by knowing that the real number belongs to a set, right, that has large Hausdorff dimension? So if you want to use Hausdorff dimension to prove a property about real numbers, if you want to use the fact that you've got some set supports a nice measure, what can you prove about the elements of that set? Well, this is what you can prove. This is a characterization of what it means to look random for such and such a measure, for a measure of a particular type. And so it gives you a kind of upper bound, a recursion theoretic upper bound on what sort of things you can prove by exhibiting sets which support regular measures. Okay, so I'm going to okay. So there's a nice case study. Right? You have a well-known notion of property of measure, right? And this is a characterization of what can you say about a real number knowing only that it is random for a measure of that type? Okay. All right, so now I want to turn to Fourier dimension, which gives an even stronger constraint on the kinds of measures that we're going to look at. So recall, the Fourier transform of a measure mu is given by this integral. Okay? So it's the transform at t is this integral of the harmonic function where t, usually t is referred to as a frequency, so t is fixed in this integral, and you take the integral of this harmonic function with respect to mu. Okay. And if for d mu you have some function f of x dx, that a sort of distribution function, then this is just the Fourier transform of that. Okay. All right. The Fourier dimension of a set A is the supremum of, well, again, once a supremum of all the s less than or equal to 1, such that there is a measure with support A, and there's a positive constant C, such that for all reals, the Fourier transform at t is less than or equal to, we need this 1 here because we have something in the denominator. So it's C times 1 plus the absolute value of t to the minus s over 2. Okay. So that's Fourier dimension. Let's go back to the Fourier transform for a second. This function is, this is a complex version of a harmonic function. Right? If you look at it when t is large, you're getting very fast oscillations of sine and cosine. Right? To say that this integral is small means that the measure is living on the negative part as much as it's living on the positive part. Right? So you're looking at these sinusoidal waves. Right? To say that this is small, going to zero as t is going to infinity, is to say that the measure is concentrating basically a lot of mass on the positive part and canceling it out with a lot of mass on the negative part. So it's not only is it distributing the mass, it's distributing the mass uniformly. Okay? All right. Okay, so it's not only is it giving you some, again, if you have a Fourier measure for dimension S, which means that it satisfies this property, then it can't have any atoms. Right? It has to distribute the mass nicely, and not only does it not concentrate mass in too many places, it has to do it smoothly and uniformly. So it's an even stronger condition on the measure than we saw with Hausdorff regularity. Okay, so, and that comes from, that observation gives you this fact. Okay, so that's one of the first things about Fourier dimension that people prove, is that the Fourier dimension of a set is a lower bound on its Hausdorff dimension. And it's not always, they're not the same necessarily. Right? The Cantor middle third set has Fourier dimension 0. It has Hausdorff dimension, as we saw, log 2 over log 3, but Fourier dimension is 0. The Cantor middle third set does not uniformly spread its mass. It has all those empty intervals sitting inside it. It's not spreading it out uniformly over all frequencies. Right? It's spreading it, but it's concentrating it as it goes. There's a pattern to the way it's spread. It's not uniformly distributed. Okay, a set A is called a Slaman set if its Fourier dimension is equal to its Hausdorff dimension. Okay. All right, and let's see an example. An example is the set of C that have effective Hausdorff dimension D. That's a Slaman set. Right? These reals, right, are uniformly spread out in the unit interval. They're not, there's plenty of them between 1/3 and 2/3. They're evenly distributed. Okay, that's the first comment, right? Is that in the end, well, we'll see a more canonical example in a few, or sort of an older, a better known example in a few minutes. The fact is, Fourier dimension is a difficult thing to compute. It's not that easy to figure out explicitly what the Fourier transform of a measure is. And there are not many known Slaman sets. Slaman had to construct one. And then there are a few that are known out of these, sort of you could think of as descriptive aspects, reals that have certain descriptive properties. And those are the canonical ones. And other than that, there's a few constructs, but they are either constructed to be Slaman sets or they're derived from these descriptive examples. Okay. So what can we say first about Fourier dimension? Okay, so this is a test of, let's try to explore a little bit and see what we can learn. Okay. So first of all, this is joint work with Alberto Marconi, Jan Reimann, Manlio Valenti. So two index set calculations. So the first is that the set of codes for closed Slaman subsets of the unit interval is a π03 complete set. Okay, so you don't have to, and it's the same sort of calculation for Hausdorff dimension. Okay, so it's not that hard to give an abstract criteria, right? Might as well, so instead of making the complexity of the set bump up the complexity of the analysis, let's take the simplest possible sets, closed sets, and to tell if the Fourier dimension is equal to the Hausdorff dimension, it's a pi03 property. Similarly, the set of real numbers such that there is a Fourier dimension making C1 random is sigma 02 complete. And both of these facts rely on the observation that the set of Fourier measures for a fixed dimension is a compact space. And then there's a pi01 set, and then you can analyze what it means to be random relative to an element of a pi01 set, and you end up with an arithmetic analysis. So you don't have to say there exists a measure and it has this nice Fourier transform. You just have to look at a kind of consistency property, which is how you apply compactness. Okay, so this doesn't really shed a lot of insight into what it actually means about C to be random for such a measure. It's just the sort of trying to optimize the definition of Fourier dimension to see by applying compactness there exists a measure. So it's a direct, yeah, go ahead. What's that? Sorry? Oh, all. I mean, it's all possible Fourier dimensions. I mean, for anything between 0 and 1. No, like you can do it between 0 and 1. It doesn't have to be. You can just. No. Yeah. The Fourier transform is just defined as it is. Okay. All right, so I ran over time in my first talk, so I tried to make sure I wouldn't do that this talk. So I may linger on these slides for a few minutes so I don't finish in 20 minutes. I mean total, 20 minutes total. Okay, so effective Fourier dimension. What's the analog? So for Hausdorff dimension, the effective Hausdorff dimension defined by Lutz and then by Riemann's theorem it gives you a complete account of when a real number is random for some S regular measure. So it gives a complete account of what it means to be a random element for a nice measure with regard to calculating Hausdorff dimension. That characterization is missing in the case of Fourier dimension. Currently there's no identified candidate for the Fourier dimension of a single real number. What one would like is to identify the sup of S such that this is a property of C, right? To identify the supremum of the S such that C is one random for a Fourier measure for dimension S, right? In terms of recursion theoretic properties of C, like effective Hausdorff dimension did for being random relative to a S regular measure. Right? So here we would like to look at a real number, right? And by looking at its so arithmetically in the real, right? Its recursion theoretic properties, its definability theoretic properties characterize what kind of measures can this real be typical for. Okay, so this is open. Right? Now I'll give you an example. So this is a joint theorem with Veronica Boettcher and Jan Riemann. We saw a reference to a theorem from R. Baker. I've learned that there's an extensive literature about these kinds of questions, which it's much bigger than I thought. So possibly this theorem was already known. I haven't found it yet, but there's a lot of papers I haven't read yet. But the theorem is this. Suppose that mu is a Fourier measure for some positive dimension, okay? And that bi is a sequence of distinct integers. Then for mu almost every real C, this sequence, bic is uniformly distributed mod 1. Okay, so if you have a Fourier measure and you have a real that's random relative to that measure, and you generate a sequence of reals from it by multiplication by distinct integers, the values of the elements of that sequence will be uniformly distributed mod 1. Okay, so for example, if bi is 2 to the I, right, then the sequence bixc would be 2 to the I times xc mod 1. It's the binary tails in the binary representation of xc. Right? For almost every xc, or for one random for the Fourier measure, that sequence is uniformly distributed, which is the same as saying that the real number is normal in base 2. But it's normal in, this is any sequence of distinct integers. It doesn't have to be powered. It's going to be absolutely normal in every base, but it'll also have further uniform distribution properties. Okay, so maybe there's an answer to this problem in terms of sort of the definability theoretic uniformity, right, in the sequences that you can generate from the given real. So maybe it could be something like that. If you have that for all these functions, if you apply the function and get a sequence of reals from xc, it's uniformly distributed. Something like that, because the Fourier transform talks not only about distributing the mass, but uniformly so. So there should be uniform distribution properties of a generic real. We just have to isolate them and prove necessary and sufficient conditions. Now, a theorem like this would be quite welcome in the study of uniform distributions, right? Because it would, as I said, there's an interesting literature and lots of calculations. We'll see some examples in a few minutes. Lots of calculations of where you use analysis to prove properties about transcendental numbers, or existence theorems about transcendental numbers. And that's sort of in the heart and soul of Diophantine approximation and analytic number theory. And so there's all sorts of estimates involving harmonic conditions. Right? And if you could identify exactly the properties of xc, so that xc is a random element of some set which has nice Fourier transform properties, right? Then you would have proven an upper bound on what kind of conclusions you can come from using arguments that involve the Fourier transform. Right, so there's lots of papers that say such and such measure has this approximation to its Fourier transform, hence the elements of the set that supports that measure are uniformly distributed under various criteria. So there's lots of theorems like that. Right? A theorem like this would be a theorem of a recursion theoretic theorem that says, if you're going to argue in that way, this is a complete account of all the properties you could possibly deduce. Right? Because this set of properties is sufficient to guarantee that there exists a measure for which the real with these properties is random. Right? So that's a kind of theorem that you can only state in terms of logic. It's a recursion theoretic completeness there. And this is the extent of what you could prove using deduced from a measure, the existence of a measure of this sort. Right? So it would give an upper bound on the kinds of theorems that one can prove in that area, which I think would be quite a welcome contribution. Okay. All right, good. Okay, so for example, there's one thing that one studies in this, when you look at Diophantine approximation, or you look at the way that the measure is distributing its mass, is suppose that you have a sequence, so this is an abstract definition. So suppose I have a sequence of reals, Cn, they're all in the interval from 0 to 1, or we can work mod 1. You can define what's called the discrepancy function for an initial segment, the first capital N many elements. The discrepancy of this sequence at capital N is the supremum of all intervals from A to B of the fraction of points in the sequence. Oh, this xi should be a ci. I don't know why I use ci there, but misprint. All right, so the discrepancy of the sequence is, look at the first capital N many elements of the sequence and see which fraction lie inside the interval from A to B. Okay, so that's the fraction of the ones that lie inside the interval from A to B. This is the length of the interval. If the sequence were perfectly distributed, right, the fraction of the elements of the sequence that lie inside the interval should be proportional to its length. It should, in fact, equal its length. Okay, the discrepancy at step n of the sequence is the soup of the difference between the fraction that actually landed inside the interval minus the length of the interval, the expected value of lying in the interval. What's that? It's I is less than or equal. Well, it's it's I is less than or equal to n. Thanks. Okay, so it's the number of elements of the sequence that lie inside the interval up to capital N divided by capital N. So that's the fraction of the ones that landed in there minus the length. Okay, so that's the discrepancy. Okay, so the discrepancy of the sequence as a function measures how well and how quickly the sequence distributes its elements. Okay, so the smaller the discrepancy, the more well distributed the elements are. Okay, so here's a question. Suppose that mu is a Fourier measure for dimension S, and that b is an integer greater than 1. So think of b as 2. 2 is an integer greater than 1. All right, so what's the mu almost everywhere discrepancy function for this sequence? So you look at the way that the tails in the binary expansion of C are distributed. And as the dimension changes, right, how does that affect the rate at which those, we know by this theorem, we know that if you have a random element for a Fourier measure, right, then the tails in the binary expansion are going to be uniformly distributed. Okay? How fast does that happen as a function of the Fourier dimension? That's the question. These kinds of calculations are known. The exact, if you ask this not about a Fourier measure mu, if you ask it for a Lebesgue measure, it's known exactly. And it's a well-studied phenomena. But if you want to parameterize the way that the uniformity of distribution occurs and parameterize it by Fourier dimension, right, then this is a nice test case. It's a nice problem to try to figure out. How does the way that the Fourier transform goes to 0 affect the properties of the typical element, right? And where the property is articulated in terms of uniform distribution. So I think this would be an interesting, both with regard to trying to figure out the global problem that I mentioned, but also just as a question about these mathematical ingredients. Okay. So now I want to turn from Fourier dimension, right, to what seems to me to be the canonical example of where Fourier dimension is applied, namely what happens in Diophantine approximation. Okay, so going back to Borel, suppose C is a real number. I want to look at three properties with regard to the representation of C in a particular base. Okay? So you can I think of the representation of C in base B as a definition of C. And so don't think of C as an element of the Cantor set. Think of it as a real number, an actual number. I mean, that can be interesting, if you think of it as an actual number. And then we have representation. We have definitions of the real number. by the base B expansions. They are particular forms of formulas in L omega 1 omega. It's an infinite conjunction. Right? It's in this interval, it's in that interval, it's in this subinterval, it's in that subinterval. So it's a way of defining a real by virtue of its base B representation. Okay, so now you could ask, what are the properties of the representation? Right? So these are ones that are quite well studied. So C is simply normal in base B if in its base B expansion, which I'm writing as C sub B, each digit appears with limiting frequency equal to 1 over B. So in binary, in the limit, you have half zeros, half ones. Right? In base 10, you have 1/10 zeros, 1/10 ones, etc. Okay? That's simple normality. It's just the expansion of digits. Normality in base B has to do not only with single digits, but with blocks of digits. Every block of digits occurs with, if the block has length L, then that block occurs with asymptotic frequency 1 over B to the L. So for a normal in base 2 number, the block 0, 1, 0 would show up 1/8 of the time, and so forth. Okay, so normal in base B is equivalent, as I mentioned, it's equivalent to saying that the sequence B to the N C, right, is uniformly distributed mod 1. So I think that's a theorem of Wall from the 1940s. So there's a connection between the infinite word that describes the real number and the symbols that appear in it, and this uniform distribution property. Okay, C is absolutely normal if it's normal to every base. All right, so good. So normality is one of the first almost everywhere theorems. Right? So Borel proved that almost all real numbers are simply normal in every base. So a random element in the sense of Lebesgue is going to be absolutely normal. And being these aspects of normality, simply normal, absolutely normal, there are particular instances of randomness. They play the role, so these properties play a role of randomness where you have to say that the real, that is simply normal, it meets the full measure sets, the sets. So being not simply normal is a measure 0 set. And to say that if you're simply normal, you have to avoid certain measure 0 sets. Okay. It's not uncommon, even for reasonably sophisticated people, to conflate randomness with normality. In fact, Rod just sent me a link to some paper by Knuth called Constructing a Random Sequence. And what was he constructing? He was constructing something that had nice equidistribution properties, namely an absolutely normal number, among other examples. So it's a stand-in. Normality is a stand-in for randomness in this world of Diophantine approximation. Okay, what's the analogy between randomness, right, in the sense that we know it of Martin-Luff randomness, right, and normality? Okay, so we started off last time by recalling that Martin-Luff randomness is equivalent to incompressibility with regard to Kolmogorov complexity. What's the analogy here? Okay? So this is a theorem by Schnorr. Well, I guess Schnorr liked proving theorems of that sort. Incompressibility is equivalent to randomness. So here he proved, jointly with Stim, that a sequence, not a real, but a sequence, is normal. That's equivalent to saying it's incompressible by any finite automata. Okay, so there is a connection between this kind of avoiding certain kind of null sets and being hard to approximate. And it scales down from Martin-Luff random and incompressible in the sense of Kolmogorov complexity, it scales down to normality and incompressible by finite automata. So there is a nice analogy that happens. What happens at the level of algorithmic information is reflected by what happens down here at the level of Diophantine approximation. Okay, so now however, there is a place where the analogy is not perfect. There's something interesting that happens here. When we talked about normality, right, we could talk about normality or simple normality with regard to different bases, base 2, base 3, etc. And that normality is a single concept. Right? What does it mean to be normal? I can define it in terms of base b, where b is varying over integers. So the criteria of being normal with regard to this base or that base or that base is a one-parameter family, right, of randomness criteria. Right? There's normality as a fixed notion, but you can interpret it for different bases. So you have a spectrum. Right? You have a spectrum where you're not changing the complexity you're not changing the kind of recursion theoretic complexity of the randomness criteria, but it's parametrized by integers. So you have one uniform mode, but you have a parameter of criteria for randomness. You can look at randomness in base 2, randomness in base 3, randomness in base 6, and so forth. Right? I don't know of an example of that in recursion theory. We change the degree of randomness, and it goes from 1 random to 2 random to 3 random. We don't have this nice one kind of randomness parameterized across a whole family. Yeah, but Schnorr randomness is not the same. It's okay, but you change the different Schnorr tests, you're changing it doesn't have the same qualitative sameness. But if you want to study that, you can. All right. So there's an old theorem. This was a question of Steinhaus. Right? So Steinhaus asked, and Cassels and Schmidt independently answered. Steinhaus's question was: is there does normality in one base imply normality in all bases? Right? So if you look random in base 2, do you look random in base 3? And the answer is no. There is a real number which is normal in one base and not in another. And in fact, stronger things are known. I don't know. I could have left it up, but I want you to listen to this first. So how did Cassels, the original proof of this fact was look at the Cantor middle third set. That set is, an element of the Cantor middle third set is definitely not normal in base 3 because the middle digit never occurs for any real inside the Cantor middle third set. Right? The first digit is either 0 or 2. This is in base 3 because you don't allow the middle third. The second digit is either 0 or 2 because you don't allow the middle third of the interval of length a third, and so forth. Okay, so being an element of the Cantor middle third set says you are definitely not normal in base 3. And Cassels and Schmidt's argument show that if you look at the uniform measure in the Cantor middle third set, right, a random real for that measure is normal for every base which is not a power of 3. Okay, so the random real for that fractal, right, looks random if you represent it in any base that's not a power of 3. And in base 3, it looks, it's completely missing one of the digits. The discrepancy is, terrible. All right, so what's the final, sort of what you could say is a complete analysis of how normality works, but the complete analysis of the dependence between normality and one base or another. So suppose you have a set of natural numbers. This is joint work with Veronica Betcher and Jan Bugeaud. Suppose you have a set of natural numbers greater than or equal to 2. So the bases, integer bases. Okay? And the following conditions hold. If I have a number b and a positive integer m, if b to the m is inside the set, then b is in the set. So if 8 is in the set, 2 is in the set, first of all. And secondly, if infinitely many powers of B are in the set, then all the powers of B are in the set. Okay, then, there is a real, so for an M like this, there is a real number C such that for every base B, C is simply normal to base B if and only if B is an M. And these are definitely necessary conditions for the conclusion that was known from the 50s. So this gives an account of how does normality between different bases work. So if you want to be, you can find a number that's simply normal to base 2, 4, 8, and not simply normal to any others, or whatever you like. You can completely mix it up. So this simple normality, and then normality is just normal in base B means you're simply normal to all the powers of B. So this gives you a full account of Schmidt's theorem as well, which was an account of what kind of patterns can you get for normality across different bases. This gives an account of what kind of patterns can you get for simple normality across bases. And there really isn't much connection. Right? The connection is if you are simply, if for infinitely many block sizes in base 2, you see that the blocks are equally distributed in the binary representation, then all the blocks in base 2 are equally distributed. And if the length 2 blocks in base 2 are equally distributed, then the single digits are equally distributed. All right, so that does show that does analyze the independence of these various independence and the extent of independence for these various metric criteria of randomness. It depends on the base in exactly this way. Now, how about compressibility? What's the metric analog of compressibility? And it's this notion of irrationality exponent, which goes back to Liouville from 19th century. So a real number C, the irrationality exponent of C is the least upper bound of the set of real numbers Z, such that for infinitely many rationals, P over Q, the distance between C and P over Q is less than 1 over Q to the Z. Okay. So this is a compression criteria. When Z is large, every time you see this rational approximation of C is less than, so suppose Z is 100, right? Then the distance between P over Q and C is less than 1 over Q to the 100. So that's a pretty good approximation to C in the scale of Q. Okay, so when Z is large, instances of this kind of inequality are instances of algorithmic compression. This is a prior but analogy to looking at compression in the sense of Kolmogorov complexity. So what's known? Yarnik and Besakovich, the set of C such that C is the irrationality exponent alpha has Hausdorff dimension 2 over alpha. And Kaufman showed that this set is a Slaman set. So not only are these reals, the compressible reals, a large fractal set, but they are uniformly distributed. And like I said, this example, when in the textbooks when they describe Fourier dimension, that's the canonical example that they give. All right, so how does compressibility in this metric sense interact with randomness in the sense of normality? There's not much of a connection. Right? Bugeaud showed that, and this is based on Kaufman's theory, Kaufman's construction. Showed that there's an absolutely normal, so it's normal, simply normal for every base, Liouville number. A Liouville number is a number so that the exponent of irrationality is infinity. So there is a number that's absolutely normal, but it has extremely good rational approximations. So it looks like there is a real separation. So incompressibility in the form of this kind of interpretation of, or in this case, high degree of compressibility does not correspond to a failure of randomness in terms of normality. They are orthogonal. Okay, so then Amu and Bugeaud asked the question about what are the possibilities? How can you get, what's an account of the possibilities of irrationality exponent versus normality? And the theorem is also joint with Becher, is that there is no connection. Take any pattern of simple normality that can be achieved, which is as described in the earlier theorem, right? And any exponent of irrationality, there is a real number which realizes both of those two things. Okay, so the patterns of simple normality give you no information about irrationality exponent. Irrationality exponent gives you no information about normality. They are completely independent. Okay, so in this context, compressibility and randomness are not equivalent. They're not even connected. Okay. However, I don't think that this theorem actually captures what we want to see. It's an interesting example, but it's not as sharp an example as I would like to see for the phenomena that we're discussing, namely being able to describe or approximate a real number and its randomness properties. The thing that we're missing here is we don't have normality has a one parameter family of notions of randomness criteria. We haven't yet looked at rational approximability, right, in terms of a parameterized family of compressibility, but it's there. Right? So as with normality, the integer bases provide a one-parameter family of compressibility criteria. You can look at a real number and ask, how well can it be approximated by dyadic rationals, or base 10 rationals, or base B rationals? Okay, so that was investigated by Amu and Bugeaud. So they defined the base B irrationality exponent of C as the least upper bound of the set of reals. This is just the definition of irrationality exponent, but I'm only allowing rationals which have denominators a power of B. So it's the exponent that tells you how well you can approximate C by rationals like that. So if B is 2, it's dyadic rationals. Okay. All right, so we have in the same way that we had a criteria, one parameter criteria for normality spanning different bases, we have a one parameter family of approximability criteria parameterized in the exact same way. Okay. There's a the first fact about this kind of thing. There is a really terrific paper by Baker and Schmidt where they give away a methodology to calculate Hausdorff dimension of sets where the set is determined by a countable family and how well the reals can be approximated by elements of that family. Right, so it works perfectly well for Hausdorff dimension, effective Hausdorff dimension, for rational approximation, for approximation by algebraic numbers. They have a quite, it takes a few minutes. Yeah, go ahead. Well, no, they're not the same. No, well, let's see. So maybe I don't understand the question. So hang on to the question. I'm going to state a theorem in a minute, and then we'll see if it helps. Okay, so Baker and Schmidt have this nice way to calculate Hausdorff dimension for sets that can be approximated by elements from some countable basis. And you can use their method to show that the base B irrationality exponent alpha, the set of C that have base B irrationality exponent alpha has Hausdorff dimension 1 over alpha. Okay, so let me see if this, I'll come back to you in a second, Joe. Here's the theorem that I wanted to mention. Suppose that B1 and B2 are multiplicatively independent bases, and suppose that A2 and A3 are greater than this fixed lower bound. Then there's a real number whose base B and base 2 exponents of irrationality are A2 and A3 respectively. So you can fix modulo problems at small dimension. You can make the exponents of irrationality across different bases anything you want. And in fact, they did it not just for 2, they did it for, look at all the bases, and you can independently modulo this constraint, assign the irrationality exponent for base B as you wish. And the only thing that happens is if you are assigning exponent of irrationality differently from B1 and B2, right, you better know that that they are multiplicatively independent, that they don't have a common power. So you can assign base 2, base 3, base 6, base 2, 3, 5, 6, 7, 10, and so forth independently, however you like. So if the base, question? Yeah, as long as the exponents that you're using are bigger than this, you can assign them arbitrarily across multiplicatively independent bases. So if the assignment goes to infinity, then you're going to get a Liouville number. But that's how it is. So the thing that happens with exponent of irrationality, the classical notion is, so normality says for every base something happens. Liouville number says for every n there is a base such that you can get at least. There are two things. There's a universal quantifier in each case. One is a quantifier over bases, and the other one is a quantifier over instances. But you're allowed to use a new base with each instance. Okay? So I'm trying to invert that and look at irrationality exponent in a base-dependent way. What's that? Oh yeah. So if you take all the multiplicatively independent bases, you can assign as you wish for all of them. That's what this theorem is. This is a special case, but yes, you can assign irrational exponents provided they're all bigger than this across multiplicatively independent bases arbitrarily. That's their theorem. Okay. So that leads to the question. So there you could see independence across bases for irrationality exponent, and we have independence subject to the criteria that I mentioned for normality. So how does compressibility with regard to one base compare to normality with regard to another? So there's not much known. I only know this one example. Okay, so there is a real number C which is normal in base 2 and whose base 10 exponent of irrationality is equal to infinity. So from the point of view of base 10, it's a Liouville number. It can be arbitrarily well approximated by decimal fractions. So that means that you're going to have, for each k, you're going to have some initial segment of the decimal expansion, say it has length L, and then you're going to have k times L many zeros. And that's going to happen, that happens throughout the decimal expansion of the real, that there are these huge expanses of zeros, because those correspond to the really good decimal approximations to the real number. Okay, so, but in base 2, it's normal. The digits are occurring, the patterns of digits are occurring in a uniformly distributed way. So it looks, in the metric sense, random in base 2, and infinitely compressible in base 10. The proof of this uses a version of what are called Stoneham numbers. And it's only, these kinds of numbers, they rest on a pattern of digits. The only 2 and 10 was not chosen by accident. Right? It's the way that the argument works is that the base to which you're going to be normal has to be prime, and the base to which you're not going to be normal has to be that prime times another prime. And that's the kind of real that you can construct. It's very particular to the way that the number theory works. So I don't know the answer to the following: is there a real number which is normal in base 2 and has infinite exponent of irrationality in base 3? So that problem touches on all kinds of this area has interesting intersections with lots of different parts of math, and so the looking at the transformation multiplication by base by 2 mod 1, multiplication by 3 mod 1. There's all kinds of issues as to how those transformations interact with each other and what it means to be invariant under them and so on and so forth. So this is a real mystery. This looking at what happens in connections between base 2 and base 3, completely open, and trying to give a kind of very canonical example of a number that's normal in base 2 and also normal in base 3 is open. And there are computable examples, but there's no kind of number theoretically insightful example. Okay, so that's the math that I wanted to discuss in these talks. My last comment is more as a cheerleader, I guess. So I think that the perspective that we get in recursion theory is unique. I mean, we do it in a very particular way, but there is a point of view in recursion theory which is I don't know, it's characteristic of our subject, right? To look at how the means that we have to analyze problems and figure out what you can do with them and the full extent, where they end, where there are certain kinds of conclusions you can't strengthen it using just these means, or you can't give a better description than the one that is formulated this way. This kind of perspective of logic and analysis of methodology and the extent to which the scope of that methodology and giving upper bounds on that. I think that's part of our field. And that's what we bring to other areas when we decide we're going to look at problems in those areas, right? And that point of view is not well understood in those areas. Of course, they have their own way of thinking about things and organizing their thoughts. So for us, that's an empowering thing. And when you decide, you're going to investigate something for the first time, then you bring, even though you don't know about that material before you start looking at it, you do bring a certain kind of expertise and perspective that is value added. So have at it. I think higher recursion theory is where you find it. Right? And if you go looking for it, you're going to find it everywhere you look. So I'll see you out there. Yeah, go ahead. One over 3 to the end, yeah? No, almost nothing like this is known. It's the extent of what's not known is basically what's illustrated here. Right? This is a picture of what's not known. So it's almost impossible. Yeah. So, like for example, it's conjectured every algebraic irrational number is absolutely normal. It's not known either way for any example. It's not even known, as far as I know, whether whether have at it, have at it. It's just not known. I mean, look at the thing that has to be proven in these things is you have to show that there are, you'd have to show, right, that there are something like random in base 2, random dyadic reals that are well approximated by these triadic fractions that you're writing down. And that's what you have to prove. I mean, it does, in the end, come down to a sequence of finite instances where you have something that looks random in base 2 is very well approximated by a triadic fraction. I don't think anybody believes anything about that. It's just completely open. I think, well, let's see. So I think it's less likely. But that's just one person's opinion, because you're getting a much higher degree of approximation. But that's the problem. And like I said, this kind of base 2, base 3 problem is notoriously easy to ask questions about it, and which are impossible to answer by current technology. It's very basic kind of questions, and it's completely open. This of normal to, yeah, so it's normal to base 2 is a pi 0 3 complete. Right? That's a good question. I don't know. No, I don't know. It's because this example is so particular, right? Yeah, you can't. Well, yeah. So, yeah, it is a pi 0 2 set. Yeah. I guess you could probably make it pi 0 2 complete, but I don't know better than that. Measures. Yeah. Yeah. Uh-huh. Mm-hmm. Yeah, that's true. That's true. Just like there's generalizations of Hausdorff dimension. Sure. Yeah, right. Right. Not that I know of. Yeah, Fourier dimension is getting it at a different qualitative feature. So it's for example, yeah. So I when I was trying to think about this in a completely uninformed state. Now I'm barely informed, but in a completely uninformed state, I thought maybe this Baker-Schmidt way of calculating Hausdorff dimension might say something about Fourier dimension, because it is Fourier dimension. So the Baker-Schmidt gives a way to calculate Hausdorff dimension for sets of reals that can be approximated in a certain way. Yeah, no, it's quite a yes. No, it's quite a general formulation. But I thought maybe that will inform us somehow about Fourier dimension. And so I asked an analyst colleague of mine, and he just absolutely, without batting an eye, he didn't care to see the definition. He said, no, there's no metric. No metric criteria is going to say anything about Fourier dimension. He didn't even want to talk about it. And so then I worked for a while and finally figured out that, well, for example, Baker-Schmidt gives us dyadically approximable, have the appropriate Hausdorff dimension, but dyadically approximable are not normal, and so that it has Fourier dimension 0. So any of these metric things seem to have nothing to do with Fourier dimension. Fourier dimension is getting to the uniformity of the distribution of the measure. So that's what makes it interesting. Right? Well, yeah, it's a lower bound on the Hausdorff dimension. Yeah. Yeah. Well, the Fourier dimension, like I said, it is a lower bound on fractal dimension, so it is giving you some information about the fractal dimension. But that's dimension is just a word that people use. In this case, it's a notion of dimension because the analysts say it's a dimension. It's not a metric. It's not based on a metric intuition. It's an analytic. It's an analytic feature. Are there any what? Sorry? Yeah, that, and I don't know. So I don't know. I don't know enough about it except basically I've told you every single thing I know. There are strange features of how it works. There's ways in which it's not additive, and there are some strange features about it. So in some ways it looks better than Hausdorff dimension. In some ways it looks a lot worse. Okay.